Today's video is going to cover using trigonometry identities to be able to prove statements. There are two main strategies that we use to prove these identities to be true. The first one is if you have one side that looks more complicated, it's always going to be easier to simplify that side and turn it into the more basic side. The other strategy, and I like to do both of these at the same time, is to change everything in terms of sine and cosine and then work from there. There's sometimes some manipulation we'll do at the beginning before switching it to sine and cosine, um, but it's easiest usually to switch everything to sine and cosine. And the most important thing to note is that so long as the two sides end up the same, the identity is true. So if you do a little bit of work on the right side, a little bit of work on the left side, and they meet in the middle somewhere, that is a fine way to do it. For these identities in this video, I have not actually solved any of them yet. I'm confident that I can prove them, but I wanted to be able to take you through my actual thought process of what strategy I use, what property I use. So I haven't done these yet. So we'll see how that goes. Okay, the other thing to note is these are the identities that we have at our disposal and we'll be using for these, right? Our ratio identities, just knowing what tangent, cotangent, secant, and cosecant are in terms of sine and cosine. The Pythagorean identities, and also maybe manipulating them. One thing we haven't talked a ton about with these Pythagorean identities is the fact that you can manipulate them to look like other things. So if I take this function here and I divide everything by cosine, if I divide everything by cosine, sine over cosine, cosine squared. Sine over cosine squared is tangent squared. Cosine squared over cosine squared is 1. 1 over cosine squared is secant squared. So that's kind of where these come in. So you can use those before you turn everything into sine and cosine. Another thing you can do is you can solve for another term, right? So if I was to subtract sine squared of theta from both sides, that would give me the identity that cosine squared of theta is equal to 1 minus sine squared of theta. So a lot of times what we've been doing is we've been taking the 1 and replacing it with this and then canceling and simplifying, and that works just fine. But you can also solve and manipulate these identities on this sheet as well. All right, let's jump in. Okay. First one is sine of theta over tangent of theta plus cosine of theta over cotangent of theta. And normally I would want to add the fractions immediately. This is definitely the more complicated side, so I'm going to start working with it first. Right, there's really not much to change about this side over here. We're hopeful that we can just turn the left-hand side into sine of theta plus cosine of theta. So when I look at this, I'm often like, okay, let me make a common denominator and add them. And at first I'm thinking, okay, maybe I should keep them in terms of cotangent and tangent while I do that because I don't want to make like a fraction common denominator. And so I start to picture that in my head. I'm like, okay, a fraction common denominator, that would be wild. But then I realize that before I even add these fractions, I can simplify each individual fraction and see if anything's going to cancel. So the first thing I am going to do is switch everything into sine and cosine. So I'll have sine of theta over sine of theta over cosine theta plus cosine theta over cosine theta sine theta. And because my final answer is just sine plus cosine, that encourages me to see if I can cancel here because I already have two things being added together, right? So if I can turn this into sine or cosine, this into the other one, then it gets me my answer. So with each individual fraction, I have a fraction divided by a fraction. So I will keep the numerator, change it to multiplication, and flip the denominator. Keep the numerator, that's a weird theta, keep the numerator, change to multiplication, and flip the denominator. And we will see in both of these, the denominator cancels, we have cosine of theta plus sine of theta, which is the same thing as sine of theta plus cosine theta. And so this one is done. Okay, you probably could have gotten to the same spot, honestly, with making a common denominator and adding them, but it was probably a lot messier. Okay, so again, oftentimes I like play it out in my head before I actually do it. So I picture like what would happen if I made this a common denominator. And in this one, I pictured a really, really messy problem and didn't want to do that. So I tried something else. Okay, this one is a little tricky because we don't know what we're trying to get it equal to, right? We just know it has to equal something, but we're not exactly sure what we're trying to get it equal to, which is a little concerning, but let's just see how things can simplify. Okay, again, I am seeing a fraction, two fractions. And oftentimes, my first instinct when I see two fractions like this, it is to try and get a common denominator. So I'm going to play this one out for you. I think this one's going to be messy as well, so I'm actually probably going to want to try something a little different. But let's play it out. Let's see what happens. Okay, so that would mean I have 1 plus cosine theta over sine theta. I would have to multiply this one by 1 minus cosine squared theta over 1 minus cosine squared theta. And then this one, sine of theta over 1 minus cosine squared theta. I would have to replace that, or multiply that, by sine of theta, by sine of theta over sine of theta. And okay, fine, I could do that. This doesn't really concern me, right? This would simplify to sine squared of theta. This is what concerns me. This is what I don't want to do. I do not want to multiply that out because if I multiply that out, I am going to end up with cosine cubed, right? When I FOIL and I get to the L and I multiply these two together, I'm going to get cosine cubed, which I'm just not, I don't have any properties that have anything to do with cosine cubed. I doubt the simplest form is going to be cosine cubed. So I am going to abandon this mission. I am not going to get a common denominator and add them because that is seemingly going to get me something more complicated when the question is kind of asking me to simplify. It's definitely giving me something that is more complicated. So we will abandon this mission and hope that we can find something better in another method. Okay, so now my method is going to be, oh, I see a cosine squared and a 1 floating around. That, rings bells for me that I need to use the Pythagorean identity. That tells me, hey, you should use the Pythagorean identity or try to use it, right? It's not necessarily, always going to work, but it is worth a try. Okay? So I showed you this on the earlier slide, but our Pythagorean identity, a lot of what we've been doing is taking this part and replacing it where we see a 1. And honestly, that works. But keep in mind that this is also a true statement. So you can kind of just right off the bat take 1 minus cosine squared and replace it with sine squared. And the reason I say that it's helpful to think about it this way is because once you start to recognize this as an identity, when you see this, it'll tell you, oh, I should replace this with sine squared. But in the spirit of doing it how we've been doing it, I'll replace the whole thing with 1, or I'll replace the 1 with the whole thing so you can kind of see that happen. Okay, so I'm going to take the 1 here and I'm going to replace it with cosine squared theta plus sine squared theta. Okay, so that I'm going to replace it with minus cosine squared theta. And then you can see it's going to start coming together a lot nicer. We want things to get simpler. Sometimes things will look a little more complicated before they get simple, um, but our end goal is simplifying. And we can see here cosine squared minus cosine squared is going to cancel. So I'll be left with sine squared of theta. I could make a common denominator at this point by multiplying this side by sine over sine, and you would probably get to the same place in the end. But you can also notice that sine divided by sine squared is going to be 1 over sine. So now I have 1 plus cosine of theta over sine of theta minus 1 over sine of theta. Now I can add my fractions. My 1 minus 1 cancels. I will then have cosine of theta over sine of theta, which is cotangent of theta, which looks pretty simple to me. Looks pretty simple to me. Okay? And that is how we do that one. Okay, verify the identity as true or false. And with this one, we're going to want to use our double angle formulas, our double angle identities, right? So one of the strategies was change everything to be in terms of sine and cosine. But I guess I could make it and should make it more specific and say that we are talking about sine of x and cosine of x, right? Simplifying it down to that. So not having anything else happening within the function. So cosine of 2x and sine of 2x is not particularly in terms of sine and cosine. So I will take this little corner up here. I'm just going to be like, okay, just an FYI, just a reminder, cotangent of x is cosine of x over sine of x. So if I'm trying to, verify if this is true, getting the other side to be cosine of x over sine of x will do it. Okay. Sine of 2x only really has one thing it can be changed into. So we'll change that one in first. So we'll say that this becomes 2 sine of x cosine of x. And the denominator, this is where we kind of want to think about where we're going, because we have 3 different options of what we can do. Okay, we can do cosine squared of x minus sine squared of x. We could do 2 cosine squared of x minus 1, or 1 minus 2 sine squared of x. And all of these kind of come from the Pythagorean identity. Okay, so when I look at these, I notice that, like, I'm playing them out in my head. If I go this path, nothing happens. I don't get anything to cancel or add, no like terms that can be combined, and I can't even factor it because it's 3 terms. Okay. When I look at this path, I do have some like terms. I can combine this and I can make it, 2 minus 2 sine squared of x, and then I could factor out a 2, 1 minus sine squared of x, and then I could, replace the 1 with cosine squared of x plus sine squared of x. My sine squares would cancel. I would have 2 cosine squared in the bottom, and that would actually work. I'd be done. But there's a faster way to do this, because when I see this one, the ones just immediately cancel. And instead of having to do all of that work to be left with 2 cosine squared of x, I can just use that one and it will work. Okay, so either of those ways I just said will actually work, but I'm in the business of the fastest way, and the fastest way for me is to play it out in my head and pick the best one. But if the fastest way for you is to just try one, oftentimes many of them will work. It's just about, the length of time it will take. So we'll see our 1's cancel. So now I have 2 sine of x cosine of x all over 2 cosine squared of x, and I can start canceling because everything's being multiplied together. So 2 divided by 2 cancels, cosine divided by cosine cancels, and I am left with sine of x over cosine of x. So, unfortunately, after all of that work, we have simply verified that this is false. Okay, these two are not equal. But this is what the left-hand side, ooh, why did I do that? This is what the left-hand side simplified to, and this is what the right-hand side simplified to. Oh, we got a circle there. All right, do we got any more? Yes. Okay, this one, they're saying it is cotangent. It is cotangent of theta. Can we make the other side equal to that? Again, a lot of these are using the strategy where you have a more complicated side so you can simplify it down to the easier side. Okay, so I'm gonna really, I'm gonna put my line here because I don't have a ton of work to do with cotangent of theta. Right, again, I'll just change it into cosine of theta over sine of theta because it's a little easier to work with things like that. Okay. Let's just go for it. I could use these Pythagorean identities down here. I could use those, but those aren't really at the front of my mind. They're not something I, play around with too much. So I'm just going to put everything into sine and cosine and see what happens. Okay, here we go. I don't know if I'm ready for this. 1 plus cosine squared theta over sine squared theta times sine of theta over cosine of theta. Okay, we got to pay attention to what's squared, what's not. All over, that's going to be all over 1 plus sine squared theta over cosine squared theta. So, couple things I am going to do. I'm going to distribute the top. I'm going to distribute in the top and also give myself some more room to do that. So when I distribute in the top, I'll get sine of theta over cosine theta plus sine theta cosine squared theta over sine squared theta cosine theta. So that's awesome because we can cancel some things. So that's just cosine over sine. And then in the denominator, I need to make a common denominator. So I will do cosine squared of theta over cosine squared of theta, right? Because when I'm going to have a fraction over a fraction or a fraction within a fraction, I'm going to want to have it be a single fraction over a single fraction, right? I don't want to keep change flip with multiple fractions. So that will give me cosine squared theta plus sine squared theta all over cosine squared theta. Immediately, I recognize this numerator here as the Pythagorean identity. So that's going to cancel out and just be 1. Okay, so let's write what we have. It is important that it's very clear what you're doing and what you have. It's very easy to get mixed up. All over 1 over cosine squared theta. Okay. Let's make a common denominator. I'm going to multiply by sine of theta over sine of theta, cosine of theta over cosine of theta. That's going to give me sine squared theta plus cosine squared theta all over cosine theta sine theta. Okay, so I just added, that's just my numerator, right? That is just my numerator. All over 1 over cosine squared theta. And honestly, as I'm doing these, I'm kind of jumping one step ahead in my head to see if the path I'm going down is going to get me anywhere. So I saw that this would again go to 1. So I have 1 over cosine theta sine theta all over 1 over cosine squared theta. Now I have a single fraction over a single fraction, so I'm going to keep change flip. I'm going to keep the numerator, change to multiplication, and flip the denominator. Move that down so it's a little out of the way. Uh-oh, I took the C with me. Then, why did I write sine squared? I was like, that is not going to cancel. Okay, now we're cooking. Now we're getting where we want. Now I can see that a cosine is going to cancel. So I guess I should only cross out the square up here. And I'm going to be left with, finally, cosine of theta over sine of theta. And my left-hand side does equal my right-hand side. So we can call this one done. All right, I think I have one more of these. Oh boy. Okay, use trigonometric identities to simplify the expression as much as possible. Okay, the bottom just simplifies to 1. Okay, we can just get rid of the bottom. That's nice, right? The bottom equals 1. So all I'm actually simplifying is this. Okay, that is not. I was worried we were going to have to do the same thing we did here with the fractions over the fractions, and I was about to skip this problem, being honest. Okay, that seems manageable. I'm going to change everything in terms of sine and cosine. So this will be 1 over cosine squared of x minus sine squared of x over cosine squared of x. Oh, lovely. They already have a common denominator. 1 minus sine squared of x all over cosine squared of x. Again, kind of like we talked about here, if you recognize this, or the similar one where it's 1 minus sine squared equals cosine, you can change it out, but you can also just replace the 1, right, with what we just did kind of above, the sine squared x plus cosine squared x. That's going to be sine squared x minus cosine squared x, just kidding, plus cosine squared x minus sine squared x all over cosine squared x. My sine squareds will cancel. Cosine squared x over cosine squared x will cancel, and that big, long, ugly thing is just 1. And we're done. I'm done. Those are my examples. Hope it helped.